This is the point where we're actually going to talk about real gases and the behavior of real gases. So it turns out gases behave ideally only under certain conditions, and those conditions, in fact, include mostly room temperature and atmospheric pressure. But but if the pressure is high or the temperature is low, real gases don't behave like ideal gases. This is because kinetic molecular theory assumes no attraction between molecules, and gas molecules don't occupy any volume, which both of those things actually we know are not true. Because if there were no attraction between gas molecules, when you cooled them down, they wouldn't turn into a liquid, right? So the default state of matter without intermolecular forces would always be a gas, but because there are intermolecular forces, attractions between molecules, they tend to coalesce and to form liquids and solids, right? So we can see some discrepancies in ideal behavior when we look at the molar volume of gases at STP. So this is something that people measure. And ideal gas behavior says 22.41 liters. And for gases like nitrogen, neon, and hydrogen, they actually give us fairly good agreement with ideal behavior. Even ammonia gives us pretty good agreement with ideal behavior. But as molecules become bigger, it turns out the molar volume of a gas can be significantly different. And by bigger, you can just look at the molecular weight of these molecules and how they're composed. The ideal molar volume falls off quite a bit. So it turns out um, that the size of a molecule becomes relatively important when the pressures are high. And think about what that means, right? Gases are traveling around in a container, and in the ideal gas behavior, there's no other molecules in the container that occupy any of the space. But as the pressure gets higher, that means the density is higher, and there'll be more molecules per unit volume. So this is a graph of molar volume of argon as a function of pressure. And at low pressures, argon matches ideal behavior. And then as you get to higher pressures, the molar volume is larger than the ideal volume simply because argon molecules occupy some of the volume. Okay, so at high pressure, it says volume is higher than predicted because the molecules actually have a volume, and if you pack enough of them into space, it becomes a significant portion of the volume. So high pressure volume is larger because molecules have volume. Now, if we look at the effective temperature, okay, we can look at ideal pressure, predicted pressures, as a function of temperature. And again, for xenon, at very high temperatures, the pressure is exactly what you predict it to be. Okay. Now, as you lower the temperature, what ends up happening is xenon's pressure becomes lower than the ideal pressure. The reason for this, right, is because they're attracted to each other. The molecules actually have forces of attraction towards each other. And because they're attracted to each other, they don't strike the walls with the same amount of force. Okay. So, how do we summarize what this means? It basically just means this: if you're at high temperature or you're at low pressures, gases will behave ideally, and that's true for all gases. But if you're at high pressures, on this end of the spectrum, or at low temperatures, that is this end of this spectrum, you should expect non-ideal behavior. Now, There was a guy, his name was van der Waals, and he came up with a version of the ideal gas equation to try to take these factors into account. So he created what's actually known as a Waals equation. It's just it means a virtual equation. He tried to put variables together that made sense. And so he basically said, well, actual pressures will be lower than ideal pressures, and then he put some terms together, including the volume of the container, the number of moles in the container, and a coefficient that he called A, right? And then he rearranged this equation to say the ideal pressure would be equal to the actual pressure plus this small term, and this is to take into account the intermolecular forces between gas molecules. He also said, well, the actual volume the volume available to the molecules is actually smaller than the ideal volume because molecules occupy space, and this is the factor that takes that into account, that molecules are occupying space. He rearranged it and was able to write the ideal volume is the actual volume minus this molecular volume that's here, and he wrote another equation based off this, which has become known as the van der Waals equation. And it looks like this, and I'm not going to make you use it. Okay, I know you're disappointed at this point, but I did want to go over with you what these different terms mean. So the pressure takes into account the attraction of the molecules, and the volume takes into account the volume of the molecules. The term A is the attraction term, and the term B is the volume term. And if you look at what these coefficients look like for small molecules like hydrogen or helium, right, it's smaller, and for larger molecules, CO2, it's a bigger number. So they sort of made sense, based on how van der Waals derived his equation. And it turns out molecules like H2 and helium have very, 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 very low boiling points. Is that they have very weak attractions for each other, and that's what you see in this attraction term, is that the numbers that you get for H2 and helium are much lower than you get for things like water or carbon dioxide. Now you notice how big water's attraction term is, right? That's why it's a liquid at room temperature, and all these other ones are actually gases at room temperature, or that's the way you can think of it anyways. Okay, so that's the van der Waals equation. I can't remember if there's one in the homework, but if there is one in the homework, basically all you need to do is look up the A term and the B term and plug in the number of moles and the volume, and you can calculate the other terms. Oh, and that's it for this lecture. I just added this to the end of the slides. This is actually Boyle's original data from his presentation, and if you wanted to play with the numbers, I thought it was kind of cool to have it.